So last time we talked about that the divided differences, right? The divided differences. In particular, we mentioned the three basic ones. The more complicated ones, again, we're going to do more of those in the future. But for the d plus at Tn, this again Tn is n delta t with delta t equal to some final time divided by the number of time steps, right? Time steps. The d plus at Tn is y at Tn plus 1 minus y at Tn divided by delta t, right? This is to approximate y prime at Tn. At Tn, you go to the next step, forward, right? Forward is why it's plus. The minus at Tn, you go backward, yTn minus yTn minus 1 divided by delta t. This is also to approximate y prime Tn, and this is backward, okay? Backward. All right, backward. And we introduce d0, okay? d0, which is centered, so you are going to get your 2 delta t because we're going to have one on the right or forward and one on the left or backward. The difference is 2 delta t, right, of the variable. Okay, that's pretty clear, right? I hope. Centered. So in terms of accuracy, what we do is that say you look at the d plus, all right. This is minus y of Tn divided by delta t. What is yTn? That's Tn plus delta t. I mean yTn plus 1, right? The Tn plus delta t. Okay. So next step. Minus y of Tn divided by delta t. Right? And a very simple Taylor expansion of the first guy, right? We do Taylor expansion on this guy, which would lead us to yTn, right? Plus y prime, right? Y prime at Tn times what? We have Tn plus delta t minus Tn, which gives us delta t, right? The next term is going to be y double prime at Tn divided by 2 factorial, which is 2 delta t squared, right? Roughly speaking, right? This is approximately equal to. So I'm replacing the red circle by the new red circle, and this minus y at Tn divided by delta t. Again, we just went over the Taylor series very, very slowly again, right? For I don't know how many times, and we're going to rely on this a lot for this part, for this first part. If you can do that, you're fine with most homework, right? With many homeworks. Later on, we're going to analyze the accuracy. We're going to do the so-called local truncation error. They're all Taylor expansion. So please make sure you can do this, right? Or pick up a book, or went over what I just did again. So this thing, we can cancel things yTn and cancel this yTn, right? So we're going to get y prime delta t times y prime of Tn times delta t, but divided by delta t, so we're going to get y prime Tn and Tn, right? Tn plus what? Y double prime Tn over 2 delta t squared delta t squared cancels delta t below, you're going to get delta t. Plus, what we didn't write down, the Taylor's expansion is order delta t cubed, right? The next term. Divided by delta t, you get order delta t squared. So the whole thing, by doing this little analysis, all right, the whole thing shows that the forward, the D plus, has, this guy has accuracy order delta t, right? This shows that. Because, why? Again, this part is error, so that's error, right? The error, which means this is small if delta t is small. So when you do your exercise, we know this one is also order delta t. Again, just simple Taylor expansion as we did here. For the D minus, you see the order delta t. For the centered guy, you will see it's delta t squared. It's better accuracy because of the cancellation. Again, you have to do it. You have to do it to show. All right. So we're going to move on. Again, there are more complicated ways to approximate the derivatives, but we'll cover that at a later time. All right. For now, we're going to move on to solve some ODEs. So numerical methods for ODEs is more probably like 4.3. It's not. I mean, this chapter is not chapter 4 from the book. It's a 4 key for our notes, right? So again, the idea is that, as we wrote down before last time, we have y prime is equal to f t y, right? Y prime is f t y, and we have an initial condition, the IVP, okay, initial value problem, also called Cauchy problem, okay. This is what we need to solve, and we said that for this part we're going to use y to denote the exact solution. We're going to use u to denote approximate solution, right? Approximate solution. So there are two things. One is the divided difference that we just explained, right? So one is that if we use the divided difference, right? We know that the y prime is approximately equal to y maybe at tn plus 1 minus y at tn divided by delta t, right? And we want y prime to be equal to fty. That's the equation. So this is like fty, right? fty, and what we're talking about from time level n to time level n plus 1. So if you make, again, we're doing approximations. If you make tn, t to be tn, y to be yn, for example, okay, then if you look at this, and what do we see, right? So y approximately satisfies such equation. So if delta t is small, the fty is kind of like ftn yn. Is everybody okay with that? So what do we have is that you multiply both sides by delta t and move the ytn to the right, and we come up with approximation to y. This is not exactly the exact value of y. So we're going to rewrite that as u, okay? So our u n plus 1, this is denoted by, this again is approximation of y at tn plus 1, right? So our un plus 1 is then equal to un plus delta t times f of tn un. Tn un. And we know u0 because u0, u is approximation of y, u0 is at a time level t0. We know where that's given, right? So this is y0, which is some data y sub 0. Okay, y sub 0. Which means that for maybe we use that example we did, right? The y prime is equal to 3y, right? Y prime equals 3y, and we said, you know, when y0 is 1, right? So in this case we have, okay, our un plus 1, u is to approximate y again. This is equal to un plus delta t times f. What is f? 3y, which is 3un, right? It's f of un. And we know u0 is equal to 1. So then we can proceed by approximate u1, by calculating u1, u2, u3, and so on and so forth, right? Can you see that? The formula gives us a iterative procedure. So we're going to get u1 is equal to u0 plus delta t times 3 times u0, which is 1, right? So which is 1 plus 3 delta t. Okay, 1 plus 3 delta t. What is u1? What is u2? u2 is u1 plus delta t times 3 times u1, which is 1 plus 3 delta t times u1, which becomes 1 times 3 delta t squared. Right? So in general, we have un plus 1 is equal to un plus delta t times 3 un, because f is 3u. So this is equal to 1 plus 3 delta t times un, right? Times un. So the next guy is the previous guy times 1 plus 3 delta t. Okay. And can you tell this then becomes 1 times 1 plus 3 delta t to the what power? Can you tell? So yes, this is to the n plus 1, right? Which shows that the un is 1 plus 3 delta t to the n. To the n. Okay. Now, if you remember, a not so trivial limit from calculus, we clearly see this is a great approximation. Is this good? Is un approximating y at Tn? Is that right? We know y of Tn. I hope you remember, right? We solved it. Now we give 2 examples of the ODE. Y prime is 3y. So what's the solution for that? E to the 3t, right? E to the 3t. E to the 3t. E to the 3t. And here t is Tn. So it's e to the 3Tn. And what is what is Tn? Tn is e to the 3 n delta t, right? N delta t. Tn is n times delta t. That's when I first divide it. I will talk about it. All right. Okay. So in particular, which means that at final time, the final time that we with the right end of the interval, capital T, right? The yt, right? This should be e to the 3t, right? E to the 3t, and our u at that n is what? Is 1 plus 3. 3 becomes 3t divided by n, right? Because 3 delta t becomes 3t divided by n to the power of n. To the power of n. You see what I'm doing, right? Again, the question is, u is approximating y. So u capital N is approximating y capital N, yt. So this should be equal to e to the 3t. They look so different, right?
Well, e just 1 plus 1 over x.
E is 1 plus
1 over x.
1 over x.
Am I wrong? I'm probably wrong.
You're getting there, I think. So that's one thing, right? The one thing. I mean, e is like e to the x is 1 plus x, not 1 over x. E to the x is 1 plus x squared over 2, so on and so forth. So that's good. But that's not exactly what we were using here, right? What we're using, what we're relying here is that. So this is about. We have to take the delta t to be tiny steps, and it's a good approximation, right? We can code this up at a later time. You'll see. If you decrease the time step, you're going to get better and better. But I want you to see, without coding on paper, what are we having, right? So this means the limit as n go to infinity. When n go to infinity, your delta t is a capital final time divided by n. Your delta t go to 0. Okay, so you're taking tiny time step. The limit of n goes to go to infinity. What I'm asking you is that suppose we have 1 plus 1 over n to the n. What is this limit? This is equal to e. One plus tiny number to huge power. That's not 1. And moreover, we can show that 1 plus a over n to the n for some fixed a. This limit as n go to infinity with fixed a. This is e to the a. E to the a. Again, now you have computers. You can easily check this. Right? Easily check this. It might be counterintuitive if you didn't go through what the proof of that. So the answer is yes. This is actually a good approximation. Okay. So this particular scheme there is called forward, because we're using the forward divided difference, right? Forward Euler, FE, forward Euler for ODE. Okay, forward Euler. All right. So, as you might imagine, similarly, we're going to have a backward Euler. All right, a backward Euler. which is where you're going to have your un plus 1 is equal to un plus delta t times that f. Now you replace that t by tn plus 1 and that y by un plus 1. And you still have u0 is equal to your initial condition y0. Okay, y0. So again, here I didn't write down as I did above. You can go through that. Again, we are approximating the y prime by the backward difference in d minus. Right. So I mean, it looks like the forward differencing. That's why I was emphasizing you have to know where you are sitting. So this is equal to fty. So this is fty, right? Fty. So this that's ODE, right? That's ODE. Fy prime is fty. If I let the ty to be tn plus 1, yn plus 1, then we are talking about we are sitting at n plus 1, tn plus 1. So in that case, this is a backward difference for y prime at tn plus 1, not the reference tn plus 1. So you go back to n. This is a forward difference for y prime at tn, but a backward difference of y prime at tn plus 1. If you write this as un minus 1 over delta t, right? This is equal to f of tn and un, right? Un. That'll be more obvious. But if you have to be sitting at tn, then we're going back, all right? But n is just an index. So let's see what happens if we try to apply this to the same ODE. Okay, to same ODE. So we have u0 is y0, right? For u1, what do we have? From the equation above, u1 is u0 plus delta t times f. F is 3y. So in this case, I put 3 what? So here is 3u1. But we know u0. We need to get to u1. What do we do? What do we do? Solve, exactly, right? The moment you have a condition for u1, you can solve for u1. That's the thinking of going just from evaluation to solve. If I give you a constraint, a condition, then you can always get something out of it. You have one condition, you can solve for one unknown. You have 17 conditions, you can solve for 17 unknowns. That's mathematical thinking, right? So here, we're going to get 1 minus 3 delta t u1 is equal to u0. Which means, well, it's not like a forward Euler, just evaluate. Here we for this simple equation, it ended up like we just evaluate. Okay? So our y0, what did we use? We use 1, right? This is, not here. But for our problem, this is 1. So this is like 1 over 1 minus 3 delta t. And if you work out a general formula for this particular ODE, you have un plus 1 is un plus delta t times f. F is 3 times un plus 1. So you can solve for un plus 1, which is un over what? 1 minus 3 delta t, right? Minus 3 delta t. So the next un is previous un divided by 1 minus 3 delta t. which means un plus un is equal to 1. The very first one, u0 is 1, right? 1 divided by 1 minus 3 delta t to the power of what? So this guy is un minus 1 divided by 1 minus 3 delta t. The whole thing divided by 1 minus 3 delta t. Right? And un minus 1 is un minus 2 divided by 1 over 3 delta t. And so on and so forth. In the end, it becomes u0 divided by 1 minus 3 delta t to the n plus 1. We'll talk about un plus 1. Okay? Again, the rule is that this decreases by 1, the power increases by 1. So you decrease by n plus 1, the power increases by n plus 1. Okay? That's a pattern. It's a pattern. Pattern is important. To think of this as a divided difference, and as I warned you on Tuesday, so this thing, there's an integral in the background. Okay, so the integral is that because we have this y prime is equal to fty, right? Fty. So we know the yn plus 1. The yn plus 1, I mean, this is probably not so trivial. If we know the derivative, we go from tn to tn plus 1. We get yn plus 1 is equal to yn plus the integral of y prime t dt, right? T dt. Now the question is, what are the limits? Have is that we are integrating. So to answer the question, the limits here are what? Tn to tn plus 1, right? It's definitely integral. And fundamental theorem of calculus. Again, the discrete part is the location of the next moment. It's the previous moment plus the speed times time. Okay. Of course, this can be written in many other ways, right? This is, of course, is also equal to y0 plus you from time 0 to time tn plus 1 of your y prime t dt, right? Dt. This is true. This is the integral form of the ODE. So then, if we have a numerical integration, right? If we replace this guy by numerical integration, then we're going to get, okay, the approximation to y. Now, at the moment you're using numerical integration, you're only talking about approximation. Okay, un plus 1 is equal to un plus the approximation of tn to tn plus 1 of that y prime, right? We know y prime. We're integrating y prime, but we're given as ODE fty. Right? fty. dt. Okay, dt. So one example is that what about we're integrating f. We're integrating this f, right? tn plus 1, tn plus 1, tn plus 1. Okay, and with some value. So at tn. So here, for example, this is f of tn un. This is f at tn un plus 1. All right, it's f of ty. Approximately, y is u. Okay, what is u? What is u? All right. So if we're going to
Is the second one f of tn plus 1 or just
tn plus 1, that's right, thank you. Tn plus 1. So in the future, for this part, we're going to put a superscript for f as well. So this is called fn, that's called fn plus 1. So it's approximated to the whole f, because the f is a function of t as well. F is a function of t and y is a function of t. So in total, if you get a solution of y, then f is a function of t, right? So f has a value at tn, f has a value at tn plus 1. And we need to integrate. Remember, this is the integral is about t because the whole derivative is with t. You integrate the y prime, right, dt. So what we're doing is that we need to calculate this little area. You agree? So if you can calculate the exact area, then you get the exact y. Ym plus 1 is equal to ym plus this area. But we cannot, so we're going to approximate it. What we did for the forward Euler is essentially we take the left hand, we take this square. Okay? But we for example, we can do the trapezoidal. If we do the trapezoidal rule, I take this, all right? I'm going to get the trapezoidal rule. Means that my un plus 1 is equal to un plus, we integrate that, which is we take 1/2 of fn and fn plus 1 times the length of the interval delta t, right? And then we of course still have this y is u0 is y0. Okay, this is y0. We use the trapezoidal rule for the integral. The whole scheme for the ODE is called is a very famous and frequently used Crank-Nicolson. Crank-Nicolson, right? So a forward Euler, backward Euler, Crank-Nicolson. Don't get confused, right? The trapezoidal is about the integration. The Crank-Nicolson is a scheme for the ODE, right? Scheme for solving ODE y prime is equal to fty. All right. So let's see what does that mean for our simple ODE, right? The same example, which means we have un plus 1, e.g. if our f is equal to 3y, right? Un plus 1 is equal to un plus 1/2 fn is 3y, right? So that's 3un plus 3un plus 1, the whole thing times delta t, right? Which means that we can simplify this, okay? You move everything of un plus 1 onto the left. This is un plus 1. Is that the factor is 1 minus, right? 1 minus the power, the coefficient in front of un plus 1 on the right. So that's 3 delta t over 2. What's on the left is what remains on the right for un is 1 plus 3 delta t over 2 un. Okay, you see that? And then un is the same factor times un minus 1. Un minus 1 is the same factor times, this un minus 2. This goes on. In the end, this is equal to 1 plus that factor 3 delta t over 2 divided by 1 minus 3 delta t over 2, the whole thing to the n plus 1's power times u0.